Hey everybody, welcome to Chem with Kate. In this video, we're going to be going over some synthesis practice problems. In this first problem, we're starting out with bromocycloheptane and ending up with 1,2-cycloheptane diol. Now let's go through our reagents one by one and infer things about their behavior. For instance, this first reagent, sodium methoxide, we should recognize by now that this is a very strong base. We should also recognize that bromine is a very good leaving group. Those two things make me think that this first step is going to be an E2 reaction. So the anion that we get from the sodium methoxide will likely deprotonate the bromocycloheptane. This bond will collapse onto there, and the bromine will be kicked off all in one step. That will generate a double bond in cycloheptene. Now that we have this reactive double bond, we can take a look at our next reagent, which you might recognize as a peroxy acid. Whenever you have a peroxy acid that is exposed to an alkene, it will result in an epoxide. Now, looking at our next reagent, we can see we have H+ in solution. That indicates acidic conditions. Whenever an epoxide is in acidic conditions, it's likely that you will see an acidic ring opening. So these lone pair electrons on the oxygen will reach out and attack that hydrogen, creating a positive formal charge on this oxygen. This bond will collapse back onto the oxygen to satisfy that formal positive charge, creating this carbocation. That leaves it open to nucleophilic attack by the water in solution. Once again, you have a positive formal charge on the oxygen here. Now remember that we are in acidic conditions, so it is perfectly acceptable for this oxygen to satisfy that positive formal charge by kicking off one of its hydrogens. We're simply regenerating the H+ that's already in solution, and that will give you your 1,2-cycloheptane diol. Now you might have recognized that this is a racemic mixture, meaning that we have both conformations of this molecule. And that all depends on the synthesis of the epoxide. Depending on what side of the ring the oxygen is added will determine what the first OH group, what side of the ring that is on, and consequently the side the water molecule will attack. So because the epoxide was created by adding oxygen to the front of the ring, oxygen was forced to attack from the back. Therefore, the second OH group is on a wedge. But if the epoxide had been formed by adding oxygen to the back of the ring, we would have come up with the second product. Our second example starts out with 2,3,4-trimethyl-3-pentanol and ends up with 2 ketones. Now, the fact that we end up with 2 ketones and there's ozone in a list of our reagents makes me think that ozonolysis is going to occur here. Now, for ozonolysis to occur, we need a double bond. Now, to create a double bond, we can go through an elimination reaction. Now, to determine whether it's E1 or E2, we can look at our first reagent, which is actually an acid, not a base. And because we'll have to work with the conjugate base, which is likely to be very weak, this is likely that this will be an E1 reaction that forms an intermediate carbocation. So, to begin, we see that this OH group is not present in our products, and so it has to be a leaving group. But OH by itself, especially in acidic conditions, which we have here, is not a good leaving group. So we'll need to modify that. The H+ that is in solution from the H2SO4 can be attacked by this oxygen, creating a oxonium ion, which is a great leaving group. It's basically a water molecule. So this formal charge on the oxygen will be satisfied by this bond when it collapses, forming this water molecule, and a tertiary carbocation there. Now, the rest of the E1 reaction, which will all happen in one step, is this conjugate base will come in and deprotonate that hydrogen. Those electrons will collapse on this bond, forming an alkene. Now, ozone is a very odd molecule. Oxygen-oxygen bonds are very weak, and it's only stabilized by its resonance. So the ozonolysis mechanism is very long and very complicated, and I'm not going to include it in this video, but you can look it up on the internet. So basically how you can think of it is that ozonolysis basically cleaves this double bond directly in the middle and adds an oxygen to each side. The third oxygen will combine with zinc to form zinc oxide. So this bond is cleaved and oxygen is added to each side, giving us our two products. In our next example, we start out with 3,4-dimethyl-1-pentyne and end with E45-dimethylhextuene. So this is obviously going to be an alkyne reduction, but we can see here that we're also going to need a chain elongation, which can be accomplished through alkylation. So we're going to start out with our sodium amide, which is a strong base. It's going to deprotonate this terminal hydrogen, giving us this lone pair of electrons to work with our next reagent, bromomethane. So as you can see, bromomethane, the bromine has a partial negative charge and the methyl group has a partial positive charge due to how electronegative bromine is. These lone pair electrons are going to come out and attack this methyl group. This accomplishes the chain elongation that we were hoping for. Next, the reduction of the alkyne is going to be accomplished with radicals. The sodium radical we have in solution is going to donate 1 electron to this carbon, and this bond here is going to donate 1 electron to this carbon and 1 electron to this carbon. Notice I'm using single-headed arrows because I'm only moving 1 electron. This is going to result in an alkene, but we have a lone pair here and a carbon radical here, which is not what we want since radicals are very reactive. So this lone pair on this carbon can reach out and attack a hydrogen from the ammonia already in solution. This hydrogen will break off and satisfy that lone pair of electrons and create this hydrogen bond. The same exact process is going to happen again with this carbon radical. The other sodium radicals in solution are going to donate 1 electron, and that will create this lone pair. That lone pair can once again reach out and attack a hydrogen from the ammonia in solution, creating this hydrogen bond, finishing off our product of E45-dimethylhextuene. And it's E because the higher priority groups are not on the same side. Our final example starts with methylcyclopentane and ends with 2-methylcyclopentanol. If you look at our third and fourth reagents, you'll see boron. That is a clear indication that a hydroboration oxidation reaction is going to occur. But in order for that to happen, we need an alkene, which can be synthesized through a free radical halogenation and an E2 reaction. So to start the free radical reaction, we're going to initiate our radical by donating 1 electron to one bromine and 1 to another to create 2 bromine radicals. This radical then can engage in propagation with this hydrogen bond donating 1 electron and this bromine radical donating 1 electron to create hydrobromic acid. This new radical species then can terminate the radical by combining with the bromine radical to create this bromine bond. Next, we can look at our next reagent and see that this is a very strong base and it will deprotonate this acidic hydrogen. These electrons will collapse here, kicking off the bromine in one step in an E2 reaction. That will give us the alkene we were after. Now we're going to focus on the hydroboration oxidation part of the reaction. Boron is a very unique element in that it does not follow the octet rule. It is only directly connected to 3 electrons. Consequently, it has this empty pi orbital. The electrons in the pi bond we just created with the alkene are going to attack this empty orbital, and boron is going to kick off this hydrogen, creating a hydrogen anion. This new bond that was created creates this group here. The hydrogen anion is then going to attack the carbocation that is briefly created, creating this group here. Now you might notice that both of these groups were added to the back of the ring, and that does make this a syn addition, but also take note that this is an anti-Markovnikov addition. And you can tell because on our alkene, we have a secondary and a tertiary carbon. And the Br2 group was added to the least substituted carbon, not the most. So moving forward, we're going to scale it back. We're basically going to zoom out for simplicity's sake. we are going to think of this entire group here as green R. That's what's happening right here. So nothing else has changed. The two yellow R's are still the same, and this entire group is now just being represented as green R. And this is just for simplicity. So remember the other reagents in solution were NaOH and hydrogen peroxide? Well, the OH in NaOH is going to grab a hydrogen off of hydrogen peroxide, giving us this species here, which is very reactive. Now remember, boron still has this empty pi orbital, and this species is going to attack this pi orbital, and boron is going to have now 4 connections, and it doesn't like that because it has this negative formal charge. To compensate for it, boron is going to kick off this green R group, and oxygen is going to grab it. So now boron only has 3 connections. Its formal charge is now compensated for, but oxygen has this positive formal charge. In order for oxygen to once again become neutral, it's going to kick off this OH group. So now we have a yellow R group and a yellow R group that have not changed, and an OR group, which was created by adding this species here and kicking off the OH. Now the OH is still in solution, and boron still has these empty orbitals. So OH is going to attack the orbital again, and to compensate, instead of kicking off another R group, it's going to kick off this OR group. So now we have the yellow R and the yellow R, which have not changed, and an OH group attached to the boron, as well as a negative OR in solution. Now, we're going to zoom back in. Do you remember this green R was this entire species? So if we zoom back in, we have this entire thing again as green R and an oxygen, which has a negative formal charge. Now we also have water in solution. And remember, we're under basic conditions. So this oxygen is going to satisfy its formal negative charge by reaching out and grabbing a hydrogen off of water molecule. This will collapse back onto oxygen, regenerating OH, which is okay because we're in basic conditions. And that will give us this OH group here, and regenerating OH in solution. So that is how we create 2-methyl cyclopentanol.